All right, we're going to get started. So, open your books to chapter 9.1, page, should be 352 in this edition. We are going to take pretty much everything that we've learned so far and mush it all together. Okay, so let's do a little bit of some reviewing. And we're going to go way back into some pre-algebra, Algebra 1. Whenever you are multiplying fractions, how do you do that? How do you multiply two fractions?
Top by top, bottom by bottom.
Perfect. Top times top, bottom times bottom. How do you add fractions?
The bottoms have to be the same.
Yes, the bottoms have to be the same. We only add the tops, but we have to have like denominators. Okay, you have to have the same common denominator, and then you add the tops and put them over that denominator. Now, what about dividing fractions? Do you remember how we divide fractions? First of all, do we like to divide fractions? No. Everybody shake your head side to side. No, we do not like to divide fractions. Therefore, we are not going to divide fractions. Yay! We're going to change that fraction, kind of turning that frown upside down, and we're going to change it into a multiplication problem, and we're going to review that a little bit here in the next couple sections. Now, we're doing all of this, we talk about fractions because that has to do with ratios or rational numbers, okay? So we're also going to implement that with polynomials because we've been working with polynomials so much. So we're going to see how we can combine both of them. And if you think in simple terms of what you've learned before about your rules with fractions, and your rules with polynomials, then this should not be complicated. Just keep it simple. Don't let a lot of letters and numbers in front of you overwhelm you and then make you think, oh, I can't do this at first glance. Take it simple step by simple step and work your way through it. It's really not that difficult. Okay? So let's begin. 9.1, we're going to go over simplifying rational expressions. A rational expression, okay, is simply a ratio or a comparison between two polynomials. We're going to be looking at two polynomials and see how they compare to each other. And by doing this, all we're really going to be doing is simplifying. Okay, we're going to have two polynomials, one compared to another, and we're going to simplify it, make it a shorter statement. Okay? So let's look at example number 1. We have excuse me, 5x squared plus 40x over 5xy plus 40y. Okay, we are comparing this polynomial or binomial with this polynomial or binomial. These are binomials. Why?
Because there's two.
Yes, because there's two terms in them. Two terms. Yes. Two. So, what we're looking for whenever we simplify fractions, especially whenever we have more than one term present, we have to find what is common in all of the terms. And then we can factor that out. Okay, so at first glance, what do you see is common in all 4 of the terms that we can factor out?
5.
A 5, yes, very good. There is a 5 here, here, let me clarify, a factor of 5, here, 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 and here. So we can rename this whenever we take out a 5 out of all of them, then this will be left with x squared, because it'd be 5 times 1, so 1x squared, plus 8x over xy plus 8y. Okay? Now, this brings us to an interesting situation. So we started here. I'm going to move this up over here so we can see what we began with. But I want to isolate this problem right now. And just have x squared plus 8x over xy plus 8y. Now here, what do we think might be common in both of these? The top and the bottom, where all the terms are involved. X? Good. Okay, that's what most people will see. What is the problem with x being a factor in all of them? Where is it not a factor?
8y.
8y. That's correct. So what are we seeing, or do we see a pattern that exists to where we can rename these and find something that is a common factor in both the top and the bottom? How do you think we could rename them?
Canceling out.
Okay, how so?
And the 8x cancel out the x, and then on the xy cancel out the x.
Well, typically you can when there's only one term on both the top and the bottom, but it has to be consistent with all of the terms. So because there's not an x in this one right here, we can't simply remove x out of all of them. Okay? But there is a way that we can rename this, making the same statement.
Multiply it all by x.
You can multiply it all by x in order to factor out the x.
So there's like
Exactly. So you're right back where you started from.
Can you do xy maybe? Multiply xy.
You could, but whenever you multiply by something, then you're still kind of making it bigger as opposed to making it smaller. It's really good to think about that because, in fact, hold on to that because in the next one or two sections, we're actually going to need to do that. We're going to have to multiply by something in order to get similar terms and accomplish our mission. What about this? Can we rename this as So here we took this binomial and we broke it down into pieces. Let's just focus on this top right here. Well, they both have an x. Well, let's remove the x out of both of them and pull it out to the side. Now, we can't eliminate it, but we can rename this binomial as x times x plus 8. And then doing the same thing down here. There's a y common in both of them. Well, let's pull the y out and see what we're left with. Well, whenever we move the y, then it's y times x plus y times 8. Does everybody see how we got from here to here? Shake your head no if you don't understand. Okay? So let's focus on just this part right here. What is common in both of them?
X.
An x. So what we can do is rename just this part here as x on the outside of parentheses, x plus 8. Now to go back from the here, you simply use your distributive property. It's x times x, which is x squared, and x times 8, so plus 8x, which is where we began. Okay, so we can take that and take it in reverse and end up with this. We do the same thing with a y down here. Now let's just focus on the bottom part. Okay, and then we can take a y out, put the y on the outside of the parentheses, and it's just x plus 8. Now we have x plus 8 as a common term in both of them that we can factor out. Because as of right now, this becomes pretty much one term because of the multiplication that's taking place, the grouping and the multiplication. So what we have here is we can factor out x plus 8, and we are simply left with x over y. Now, we cannot simplify this anymore. So, and we've used all of these steps before. Okay, we've gone from this to this. We've also started from this position and renamed it in this format. Both of those are saying the same thing. It's just putting it in a different light. Again, using the example, if you have Sheila standing here, well, then you rename her as Barbara. It's still Sheila, you just gave her a different name. Everything about her is the same, you just gave her a different name. Okay, we renamed this. All right, everybody good so far? Cool. All right, example number 2. 126a to the third minus 126a squared b over 84a squared plus 84ab. Okay. So here we have to figure out, well, chances are we already know simply because these are all even, there is a factor that goes into all of them, right? Now, if you don't know what factor is common with them, well then that's whenever we use the factor tree for both of them and find out what factors are common in both. Okay, do y'all remember this? We'll review it a little bit. So we have 126, and we know that that is going to be 2 and 63. And then this will be 9 and 7, and then 3 and 3. So we have 2, 3, 3, and 7. Then we have 84, which will end up being 2 and 42. And then 7 and what? 7? Are you sure?
Mm-hmm.
Yeah, okay, awesome. And then 2 and 3. All right, so we're going to circle our common factors. We got 2, 2, a 7, a 7, a 3, and a 3. So what's left over is going to be 2 from 84 and 3's from 126. So let's go ahead and rename that as 3, a to the third minus 3a squared b over 2a squared plus 2ab. Okay, does everybody see how we got from here to here? We did factor trees for both 126 and 84. We found out which ones were common in both of them and removed them and left what was left over. We keep what is left over, and that stays plugged in, kind of like the x and the y that we had left over. Okay, we can't simplify that anymore. Now that we've done the constants, now let's work over on the variables. What do we have that's constant in all of them? Anybody? A. Very good. There's an A, at least one A in all of them. We can go through and check. There's A to the third, A to the second, A to the second, well, A to the first, so that's the lowest one is the most that we can take out. So now we have 3a squared minus 3ab over 2a plus 2b. Okay? Do you see anything else that can be factored out of that? You want it to be. You think it should be, especially after the last example, right? Well, they did it in the other one, I didn't see it, so what about this one? The book shows you two different forms that you can put this, notice you can actually, if you look at the individual numerator and the individual denominator, you can actually factor out or rename this where you have 3a times a minus b, or you can factor out a 2 here and you have a 2 times a plus b. And even though that's renamed, we are still not finding like terms that can be factored out. There are no more common factors actually there. Even though we renamed it from this to this helps us see a little bit more clearly if there's any other possible factors that exist and there are not. So either one of these methods will be satisfactory for the answer to this question. Okay? So now what I want everybody to do is do number 3. Everybody close your books. Close your books, no looking, no peeky. Or at least cover up your book where you can't see it. And I want everybody to, you will do number 3 on your own, but I'm going to write it up on the board. Okay?
Is this problem 3 or example?
It'll be example 3. So don't look, I will write it up on the board and you process through it. See what you can come up with. 4x to the 4th plus x to the 3rd minus 6x squared over x squared minus 2x. Then set your pencils down whenever you are done, or think you're done. I will give you a hint of some sort. If you are told to simplify 8 over 4, what does that give you? What's the answer? Okay, so you have 2 over 1, which also equals just 2, right? Okay. Give you about 30 more seconds. Authority. Put that pencil down like you know it. Is that annoying? Am I ready? Good mathematicians know how to deal with pressure. No pressure. I know y'all strive to be good mathematicians. Okay, so let's get started. For those of you that have completed it, what answer did you come up with?
Should I tell you?
Yes.
I don't think it's fine.
Okay, well, still tell me.
X on the X, open parentheses, X squared plus X minus 3 close parentheses.
Plus X.
Minus 3
Okay.
over X minus
Over
1. X minus 1.
X minus 1. Okay. Interesting.
I just came up with X on the bottom.
Okay, so you have the same top, but just X on the bottom.
Yeah.
Okay, so we have X times X squared plus X minus 3.
Oh, because you said the 3 over the 1 just equals 3, so
Over
you can
X.
get rid of the 1.
What's that?
Because you said 3 over, like when you did the example, you said the hint, the 3 over the 1, it just equals 3.
Okay, so how does that change your answer?
You can just get rid of the 1 because it's 3 over 1. It just equals 3.
So is this what you have down?
That's what I have.
Okay, what do you have?
X parentheses X squared plus X minus 6 parentheses over X minus 2. That's what I have.
That's what you have? Okay. Anything different? Okay, so we have these 3 examples. Okay, before we go any further, okay, is this right here, this trinomial, can you factor that? Do you remember factoring it?
Yeah.
Yeah.
Probably good, but
All right. So how did we get with a 3 here? Those of you that ended up with a 3 right here, how did you end up with that? Anybody? Anyone?
Well, at the beginning it was the 6 over the 2x, and so I factored 1x out of the 3 and 1x out of the 2, and it was left with an x up at the top, and the 3 on the top and the 1 on the bottom. And
Okay. So let's stop there real quick. So you factored out a 2 from here and here. Okay. But what was it that we talked about? That if you're going to factor something out, it has to be factored out of all of the terms.
that's what I did.
How? How did you factor a 2 out of all of these?
I did.
Yeah. Yeah. Can I start over? Okay. So now we know that unfortunately these didn't make it. Let's see where we get with this. Okay, so far everybody's doing really well with, we see that there's an x, or an x squared that we can factor out of here to rename it as x squared, and it's x squared plus x minus 6. Okay, over, and here we can factor out an x from both of those to where we have x over x minus 2. Okay, does everybody agree with this so far? Okay, we've isolated the numerator and we pull out an x squared, and this is what we have left over. We isolated the denominator, pulled out an x, and we have the x, our x minus 2. Now here, since we are multiplying this, we have now turned 3 terms into essentially 1 term up top, and 2 into 1 term. Because we're grouping and multiplying, then we can actually factor out an x from one of these to where we are now just left with x. There's 1 in each of them, there's 1 left over in here. Okay? Now what's interesting about this part right here, we can actually factor x squared plus x, plus x minus 6. That will be x minus 2 times x plus 3. Okay? So, we can now rename this right here as x times x minus 2 times x plus 3 over x minus 2. Now, do we still have a common factor from the top and the bottom? What? X minus 2. So we can get rid of both of those. And we are now left, I'll go over to the side of the board over here, x times x plus 3. Over, it's technically over 1, but you don't need to do over 1. You can just leave it in this form. Okay? The book goes ahead and actually combines these. So if you see that, well, the book said it's x squared plus 3x. Well, whenever you multiply x times x, you get x squared. And plus x times 3 plus 3x. These are the same thing. Okay, they equal each other. All right? So getting to this point was really good. All right, we got here, but we can still go take some further steps. All right, so now we see a trinomial, and if you see a trinomial, especially in your homework, there's a good possibility that whenever you factor it, factoring it means you have two sets of parentheses, that one of those terms is actually going to be factorable. Okay, so be looking for that. And it's very possible to factor that a couple of different ways sometimes. And so what will help you to be looking for the right one is your hint down here. So I know I've got to factor these. You know what? This is math and they want me to learn and recognize, so chances are one of the factors is going to be x minus 2. And so that might kind of kick you in the right direction. Those little subtle hints if you're figuring out the psychology of this math book. Okay? Not the psycho of the math book, the psychology of the math book.
I think we have the psycho figured out already.
Oh, settle. All right, so we all get here?
Yeah.
I'm gonna erase this. All right, so that will kind of get us kick-started with 9.1. Now we're gonna move on to 9.2. Yay for 9.2. 9.2's been waiting so patiently. Okay, now we're going to be multiplying rational expressions. So we talked about this. How do we... Now, rational expressions, again, talking about ratios or essentially fractions, because a fraction is a comparison or a ratio of two numbers. So how do we multiply fractions? Someone else other than before? How do we multiply fractions?
The bottom has to be the same.
No, that's adding. Multiplying. Yes. Everybody say it. Top times top. Bottom times bottom. Come on. Like you're in a horrible cult. Top times top. Bottom times bottom. No, everybody say it. Seriously. Top times top. Bottom times bottom. Okay? So, which means if we have 2 over 3 times 4 over 3, it's going to equal what? Yes. 2 times top times top.
8 over 9.
8 over 9. Very good. Okay. Now, big difference, because this is a common issue. People will confuse multiplying fractions with comparing fractions. If there is an equal sign in between them, then we do what? Do y'all remember? What type of multiplication? Cross multiplication, yeah. So this would be 2 times 3 and 3 times 4. But that's not what we are doing, so don't confuse that. We're doing top times top, bottom times bottom when we multiply fractions. So, if we look at example number 1. Now, what's interesting is we're going to multiply polynomials, okay? We're going to multiply polynomials. That can be extremely hectic if you do that outright with the information that we're given. However, if you saw, say, 144 over 36 times 77 over 55. And you're not allowed to use a calculator. Oh, man, no. Do you want to calculate this? Do you want to multiply these out? 144 times 77 and then 36 times 55? No, nor should you. You can actually simplify this and make your life a whole lot easier. This fraction has a 12 that is factorable out of it, at least. 144 over 36 can be, because 12 times 12 is 144. 12 times 3 is 36. Well, actually, we'll keep it in this format for right now, just to prove a point. Well, 11 is factorable out of both of those, and that gives you 7 over 5. Which one is easier to multiply? This one? Yes, the top one for sure, absolutely. This was, we just like to do for fun, but we'll still go multiply these numbers together. So, likewise, we're going to be looking at complicated fractions. We're going to make them simple. And that's why we did 9.1 first, and then went to 9.2, and did not go in a different order.
You could still further simplify the 12 over 3.
You actually can, yes. And it's very good that you see that, because you absolutely can. So let's look at example number 1. We have 5x squared minus 5x minus 100 over 3x squared plus 6x minus 24 times 3x minus 6 over 3x. All right. Before we move along, one thing that we need to realize that we can do is whenever we are multiplying fractions, we can remove or we can factor out crossways if necessary. Okay? So whereas if we were adding or subtracting these fractions, we can only factor out the tops and the bottoms here. It's isolated factoring this and then solely this fraction over here. But whenever we multiply, if there's something factorable between this and this, then we can do that. Okay, and likewise from here to over here, we can actually do that. Well, let's first start to simplify and see what we have. This top one, what do you think at first glance can we factor out of there, or at least rename it? 5. Everybody see that?
Yeah.
Okay, so we're going to have 5 times x squared minus x minus 20. Okay, let's keep everything consistent. So what about this one?
3.
3, absolutely. So we're going to pull out a 3, and it's going to be x squared plus 2x, 8. What about this one up here? 3. Very good. We can actually pull a 3 out of this. 3, and it's x minus 2. What about this one down here?
Since the
Go ahead.
no,
Answered it?
I really see.
Okay. Well, the 3x we can't do anything else with, so we're going to leave it. Well, there's nothing more we can do. These trinomials really don't help us out, so we need to rename them and put them in binomial form. Okay, we're going to factor them into 2 binomials as opposed to 1 trinomial. Okay, just like what we did before. So we're going to keep the 5, and we have factors of negative 20 that when added together give us a negative 1. So I'm thinking we're going to have x minus 5 and x plus 4, but that's just me. Okay, so negative 5 times 4 is negative 20, and when you add negative 5 plus 4, you get negative 1. So we're good, right? All right, what about the bottom? Factors of negative 8 that give you a positive 2. What is that going to be? Factors of -8 that give you a +2 when they add together.
-2 and a +4.
Very good. A -2 and a +4. So -2 times +4 is -8, and 4 minus 2, or -2 plus 4, gives you a +2. So now we're good here. Times 3 over x minus 2 over 3x. Now from here, we've got all of this simplified as much as we can stretch it out into most basic forms, okay? Into just the pure basics, and now we can look at each one of these and start canceling stuff out and see what's left over. Okay, this is very similar to if you have x, y, z, r, t, and then you have z, t, l, m, r. Okay, factor out what's common. Well, we can factor out the z, we can factor out the t's, and we can factor out the r's, and what's left over is x, y over lm. Does everybody see how that happens? We're doing the same exact thing down here. So what is one thing on the bottom that is also on top? What's it?
X plus 4.
X plus 4. So x plus 4 here and x plus 4 here. There's one of each of those, and we're only pulling out, doing one at a time. Okay? The 3. Do you see a 3 that's common in the top and the bottom? Okay, so we can cancel out a 3. Now, do we cancel out both of these 3's? No, we do not, because we only eliminated one up top, so we can only eliminate one on the bottom. So we'll do that one. Anything else that we see common?
-2, x minus 2.
The x minus 2's. This one here on the bottom, this one here on the top. Do we see anything else? I actually think we're good. There's no other 5 that's on the bottom. There's not an x minus 5 on the bottom. There's no other 3 on the top, and there's no other x all by itself on the top. There's this x here, but if we're going to pull out this x, there has to be one with this 5 as well. Okay? So what we are left over with is 5 times x minus 5 over 3x. So we started off here, which that looks, I mean, looking at this, whenever you walk into class and I told you multiply this, you'd be, are you sick in your head or what? Because I ain't doing that.
I'll just turn around.
I agree. But now that we took our time and we broke it down into pieces, and what's interesting is I put all of this together based on what all of you said. Okay? I helped kind of guide that area, okay? But y'all are the ones that discovered this. So you can do this. All of y'all can do this. Just take it in pieces, isolate your problems, and work through that until you're done. And then do the next one. And then just stretch it out into most basic forms, and then do your process of elimination and find out what's left over. And it's that simple. Yay. All right, everybody, go team. Woohoo. All right, any questions about that? Sure? Some questions? Okay. Let's go to 9.3. Now, one thing I will say on your homework, it starts more basic than that heavy problem that we did. We did that because it encompasses a lot of what's going to be on your homework in bits of, and puts it all together. So that should be closer to one of the most complicated questions you're going to have on your homework. But you guys being able to do that, you'll be able to easily do your homework for 9.2. All right, 9.3, dividing rational expressions. Dividing rational expressions. So let's understand what we can do first, okay? What we can do, what we don't want to do. So if we have 2 over 3 divided by 5 over 7. Again, do we like to divide fractions? Everybody shake your head and say no. If you ever take a test and see where you're asked to divide a fraction by a fraction, I want to, in another town far away, hear y'all say no, like a herd of cattle, just no. All right? No, we don't like that, so we're going to change it. We take our first fraction, 2/3, change the division to multiplication, and we take the reciprocal, or we flip our second fraction, so it's now 7/5. Well, we like to multiply fractions because that's easy. So now 2 times 7 is 14, 3 times 5 is 15, and we have 14/15. This we can do, that's easy, all day long. We are going to do the same thing with our polynomials. So let's first look at our first example. Okay, so we have x squared plus x minus 6 over x minus 6 divided by x plus 3 over x squared minus 7x plus 6. First thing we're going to do, we're going to identify we are told to divide, and we don't want to do that. We are going to be rebellious and refuse to divide a fraction. That's the only time you can be rebellious in math class, by the way, is whenever we divide fractions. Otherwise, you gotta zip it and, yeah, exactly, deal with it, thank you. So we're going to rename this. We keep the first fraction, x squared plus x minus 6 over x minus 6. Okay, we kept our first fraction, change division to multiplication, and take the reciprocal, or the flip, of our other fraction. So now x squared minus 7x plus 6 over x plus 3. Now we are at where we were in 9.2. We're multiplying fractions. We will go through the same process. We will stretch these out into the most basic form and see what we can eliminate. Okay, so let's look at our first trinomial. What is a factor of -6 that when added together gives us a positive 1?
3 and 2 and -3 and
Okay,
-2 and positive.
so which one will give us a positive 1?
-2 and positive.
Very good. So we have x minus 2 times x plus 3. So we have -2 times positive 3 gets us -6, but when we add them together, we have a positive 1. That is over x minus 6 because we can't simplify that anymore. Times, now what about this one? What is a factor of positive 6 that gives us a -7?
-1 and -7. No, -1, -6.
Very good. -1 and -6. Very good. So x minus 1 times x minus 6 over x plus 3. Because -1 times -6 is positive 6, but -1 minus 6 gives you a -7. So now we are in our most basic form. Now we simply go through elimination. We see that there's an x plus 3 up top and the bottom, so we can scratch those out. X minus 6 on the bottom, and there's 1 up top. We can scratch those out. And all we are left over with, and we're going to move this up here, is x minus 2 times x minus 1. And whenever you do your questions or any test problems later on, you can leave it in this format, and I'm fine with that. Okay? If you want to, you can go ahead and do your FOIL method and combine them together. So it'd be x squared minus 3x plus 2 with no parentheses. So either one of those is going to be correct, accurate. Any questions with how we started from here and ended up with one of these answers? Questions? No? Cool. Everybody feeling a little more comfortable with it? You have plenty of opportunity to get comfortable with this. Promise. Alrighty. So we've talked about simplifying, we've talked about multiplying, we've talked about dividing. So look at example number 3, because this is kind of, or can be confusing if you let it be confusing to you. So if we have an example of this is 2/7 divided by 5/6. Oh, okay, that's just like fraction within a fraction and other fraction that's there in the fraction, and I don't like that. Well, if you don't like this, simply put it in a different format. Okay? This is the same as 2/7 divided by 5/6. That is the same thing. And then you're like, oh, okay, well I can do that. I still won't divide a fraction by a fraction, because that ain't happening. But I'll rename it to 2/7 times 6/5, and then that'll give me 12/35. And that I can do all day long. So if you see it in this format, don't get overwhelmed. Simply rename it. Get rid of this line and put in a division sign, and then work from there. Okay? Easy, easy. All right, 9.4. Adding and subtracting rational expressions. We talked about this a little bit. What must you have in order to add or subtract fractions?
Common denominator.
Yes, a common denominator. The same bottom number. Common denominator. So, if we have 1/2 plus 3/2, we get 4/4. Right? Who says yes, who says no? That is a no. Absolutely no. We cannot do that. Whenever we add fractions or subtract fractions, the bottom number stays the same. That's why you have to have a common denominator. That denominator stays the same, and then you add the numerators. So it'll be 4/2. Now we can simplify that, but what we get to first is 4/2. That denominator stays the same, and then you only add the numerator and put that on top. Okay? So now let's do this with polynomials. We will look at example number 1 first of all. Easy example of what's going on. So here we have this. The best thing I tell you to do, I think is going to visually be easier for you, is to go ahead and find what your common denominator is, which is going to be what on this?
X minus 1.
Absolutely, x minus 1. Go ahead and write that down there and draw one big line. Now what we do is we put all of these together up top. We're subtracting this from this. Okay? Now, what is interesting is whenever we do that, this negative sign applies to everything on top of here, so you have to do that as a group. Okay? This has to be a group. So we have 2x plus 5 minus 6x minus 3. That negative sign affects both of those terms. Does that make sense so far? So once again, we have to pay attention to the signs. Not the stars signs, not prophecies, but the signs. All right, so we'll rename this to 2x plus 5 minus 6x plus 3 over x minus 1. Now all we're doing is combining like terms. We're simply combining like terms. 2x minus 6x equals a minus 4x, and 5 plus 3 is 8, plus 8. This gives us x minus 1, or down at the, excuse me, the x minus 1 stays where it is. Okay, is there anything else that we can do with that? Yes or no?
Take the 4 out.
Okay, we could, all right, let's take a look at this minus 4x plus 8. We're just going to isolate that for a second, minus 4x plus 8. There are two things that we could do with this to see if there's any more to factor out of this. We can factor out a positive 4, and so that would be times minus x plus 2. Or we could factor out a minus 4, which gives us x minus 2. Okay, those are two options to renaming this. Do either of those help us eliminate this x minus 1? No, but it is very valuable to at least consider that. So the fact that you were even thinking of that it's crossing your mind, you know what, I see this and I can see I can pull a 4 out of here, or maybe even a negative 4, that is really, really good. That means you're evaluating the problem and making sure that you haven't missed something. So don't discard that. That's very, very good. It just so happens there's nothing more that we can do with this. Okay? Let's look at example number 2. Real quickly, just to kind of help, if you have 3 over 5 and plus 7 over 3, what is our common denominator? What's going to be our common denominator?
15.
Very good, 15.
Yes.
So we're going to have 15 plus 15. We know that these are going to be our common denominator. Now, we're changing each of these fractions because we've renamed the bottom. If one of these was 15, then we don't change it. Okay, but since we're having to change the 5 to a 15, we have to change the top the same way that we're changing the bottom. So in order to get 5 to 15, we had to multiply it times 3. Whatever you do to the bottom, you must do to the top. So since we multiplied 5 times 3 to get 15, we'll now multiply the 3 times 3 and we get 9. Likewise, we multiplied the 3 times 5 to get 15, so we have to multiply the 7 times 5 and we get 35. This gives us 44 over 15. Again, we keep the same denominator and we simply add the tops. The same way in whenever we're finding common denominators for polynomials, in order to get that common denominator, whatever you are having to change in one to get it common, whatever you do to the bottom, you must do to the top. Please don't forget to do that, because then you'll go through a lot of work and get it wrong because of something very, very simple that you overlooked. With that being said, let's look at example number 2. 5x plus 4 over x minus 3 plus 3x minus 1 over 3 minus x. Very interesting. What could be our common denominator? Without looking at your book, what could be our common denominator?
X minus 3.
How?
Because it's on the bottom.
Well, this is, but that's not what that is. Both of them have to be the same. So how can you make both of them the same?
Times that one by 3x.
Which one, this one or this one?
Left one.
So if you multiply this times 3x, that's going to give us 3x squared minus 9x. Is that the same as that?
No, but then you have to times the other one by x.
You multiply the second
thought.
one by -1.
-1? Why would you do that?
Because then it would change the 3 to a -3 and the x to a positive x.
Okay, well we'll kind of toy around with this idea of yours and we'll learn from it. How about that? Okay? So she's wanting to multiply this 3 minus x times -1. Okay? I don't know why you're going to do that. But anyway, so you have -1 times 3, which is -3. -1 times -x, which is positive x. Or you could rename that as x minus 3. So that was a pretty dumb idea, right? Very good. Awesome. Something as simple as a -1 changed it. And -1's easy. Always look for the easy way out instead of making it complicated. So very, very good. We simply multiplied this times -1. To rename it, you can see that, man, these are so close to each other. There's an x and a 3, and that's all. It's just one's positive, one's negative. Well, how can we change that? Okay, so simply by multiplying times -1 gets us there. Now, in doing that, whatever we do to the bottom, we have to do to the top. This one did not need to change, so it stays the same. 5x plus 4 over x minus 3 plus, now we have to multiply, we'll go ahead and put x minus 3. Off to the side, we have to multiply the top times the same thing. Okay? So this bottom one gets us here. Up here we have -1 times 3x gives us what? What? -3x?
Yes.
Yes. And -1 times -1 is a positive 2. So now we have our common denominator. We can put that down here, x minus 3. And we can put everything up top. Here's a positive, so it's not going to change this as a group. It stays the same. So 5x plus 4 minus 3x plus 2. What is 5x minus 3x? 2x, very good. And 4 plus 2 is 6. And we have over x minus 3. Okay, and there we have it. Now I know people are looking, wow, if I pull the 3 out of here, or the 2 out of here, then I've got 2 times x plus 3, but this is x minus 3. It's not going to get me anywhere, so I can just leave it like it is. But, good for you for thinking that. Yes?
No.
Were you wanting to do a -2 out of it? Did you think of that? Huh? Okay. Any questions so far? Okay. All right. Everybody have this down? We can move along? Now, with that being said, in that situation, we only had to change one of the fractions. There are times that you are going to have to change both of the bottom numbers. And so basically what's happening is you are multiplying these two together to get a common denominator, and then you will multiply this top number by the other denominator, and this numerator by the opposite denominator, so that you have your common denominator and then you add your numerators. Same denominator, add the numerators. Do not add both the top and the bottoms together. Make sense? Awesome, good job. Very good job. How many of y'all thought I was treating her like really horrible and making fun of her at the beginning? That's kind of fun though. Whatever, about her -1. That would have been rude if it didn't work out. Maybe one day I'll be in like this horrible mood and I'll just treat everybody poorly. Would that be fun? No. I'd have so many parents knock on my door. What are you doing? All right, 9.5. 9.5. We are now looking at rational functions. Ooh, functions. Raise your hand if you like functions. Come on, don't hold back. You know you do. Like them, they're functions. What do you think of whenever you hear function? Graph. Yes. It's awesome and it's so funny. Graph. Graphs. So, but graphing is easy because you pick a value for x and you solve for y. It is that simple, especially whenever you get to pick your own numbers. You can pick your nose while you're picking your own numbers, and that's fine too, as long as you pick a value for x and solve for y, and then you plot them out and connect the dots, and you see exactly what you're dealing with. So, let's look at example number 1. If you look at this example, it says the function of x equals x minus 3 over x squared plus 4x plus 3. Function of x equals x minus 3 over x squared plus 4x plus 3. Now, in this situation, we are told the values of x because we are given a list. We're told that we're going to use 0, we're going to use 3, we're going to use -1, we're going to use -2, and we're going to use -4. Okay? This is what we are going to use. Now, all we have to do in this is plug in 0 wherever we see an x. So the function of 0 equals 0 minus 3, 0 squared plus 4 times 0 plus 3. So that equals minus 3 over positive 3, which equals minus 1. Okay? We didn't even have to do any factoring. We don't have to mess with that because we're simply plugging in values for x and solving. So here we can have our little chart which helps us organize everything. So when x is 0, y is -1. And that is our coordinate point. 0 and -1. We plot that. Now we can do 3. Function of 3 equals 3 minus 3 over 3 squared plus 4 times 3 plus 3, which equals 0 over 9 plus 15, which is 24, which equals what? 7.
42.
Hike. Quick question. Anything to the power of 0 equals what?
1.
1. So chances are that's not 1. How many? So let's keep it simple. How many times does 24 go into 0?
0.
0 times. Very good. So the answer is 0. There you have it. So when x is 3, y is 0. And then you keep going on with -1, -2, -4. Here you have your coordinate point of 3 and 0, and then you just plot those points and see what this function does. You connect the dots and you can see what's taking place. Okay, that's all that is. In this case, it gave us values for x that it wants to use. Others, it may tell you to choose your own values and you get to decide which ones you want. Okay, simple, easy enough. Now, in here, this section talks about asymptotes. Asymptotes. Asymptote. Okay, if you look at page 371, 371. Now, here it's talking about example 2, and if you notice, whenever it is being plotted, that on both of those sides, both in quadrant 1, which is the top left or top right, and quadrant 3, which is bottom left, they get closer and closer and closer to both the y-axis and the x-axis. Okay? Now, whenever it is as far as the y-axis, let me erase this. As this goes along, it starts getting closer and closer and closer and closer, but never really reaches it. Okay, this axis, the y-axis here, is called the y-asymptote. Okay, it's the point at which it begins reaching it, and actually, by definition, it's the point whenever it hits 0. Okay, with y or x being 0, x is 0 whenever it hits this line. Okay, so this will be the asymptote, this will be the x-asymptote, at the point in which it actually hits or has a value of 0. Okay, so when it hits the y-axis, x is 0. Whenever it hits the x-axis, y is 0. It's neither positive nor negative, y is 0. Okay? So it's actually pretty simple. Whenever y equals 0, what does x equal? Well, that's the asymptote for that part. Whenever x equals 0, what does y equal? Well, that's the y-asymptote. Okay? Make sense? Easy enough.
I think you spelled it wrong.
Did it wrong?
Yeah.
Oh, I forgot the other T in there. Asymptote. Sorry. There was a P in there. Asymptote.
And the other P is supposed to be a T.
Oh, God.
You just messed it up.
Asymptote. Yes. Yes. Sorry. Thank you. Very, very good. Okie dokie. Now, one way to think about this is, let's look at these fractions. Which is bigger? 1/4, 1/4, or 1/32? 1/4 is larger, okay? So 1/32, if you think of a piece of pie, is a smaller piece of pie, okay? Actually very, very thin, okay? And then 1/87 is actually going to be smaller than that, okay? And as the bottom number gets larger and larger and larger, you're freaking out more and more and more because your piece is actually getting smaller and smaller and smaller. It's approaching 0, okay? Approaching 0. So whenever you deal with fractions and end up calculating them, keep that in mind that the smaller the denominator, actually the larger the piece, okay? The larger the bottom number, actually the closer to 0 you are achieving. You're getting closer to 0 the larger that denominator is. Another way to achieve the asymptote is, the larger this number is, the closer you are to getting to it, that you are to achieving that. And so just with your homework assignment, you may see it in fraction form. You may see where that larger number actually gets you closer to one of those axi, or the x-axis or the y-axis, okay? Whereas the larger number puts you further away from it, okay? All right. Let's do this. 9.6. Everybody go to 9.6? Now we're going to talk about rational equations. A rational equation is an equation that contains at least one rational expression. One rational expression. So, a rational equation means we have a rational expression and what else? It's not a statement, it's an equation. What have we not been using so far in all the stuff we've been doing? What symbol or sign have we not been using?
Common sense, what?
Pretty good. Actually, you've been using a lot of common sense. What mathematical symbol have we not been using so far?
Like the square root?
Equation.
That's what it says.
Equation. Equal sign, yes. It is supposed to say something. It's an equal sign. So now we're going to have an equation, which means we can actually calculate a value because we have an equal sign, but we're going to have a rational expression involved in it. So if we had, let's say, I don't know, example number 1 from 9.6. 18 over x minus 6 equals 6. Okay, well, we have an equation, we have a rational expression, and we actually have a polynomial involved in this as well. X minus 6 is a binomial. Okay, well, now we can actually calculate this and solve for 6, or solve for x. What would you do as a first step to solve for x, or to at least rename this? Right now we have x on the bottom, there's not much we can do with it down there. It needs to be up top. So what would you do first?
Could you multiply the fraction by,
No, keep going.
by x minus 6?
Yes, very good. We're going to take this whole thing and we want to move it up over here. But in order to do that, we've got to take the inverse operation. Right now we're dividing by x minus 6. So now we're going to multiply both sides times x minus 6. That way that cancels out. We now have 18 equals 6x minus 36. So let's start getting x all by itself. So since we're subtracting 36, we're going to add 36 to both sides. So that's 54 equals 6x. Divide by, since we're multiplying times 6 now, we're going to divide by 6 on both sides. And x will equal 9. So we had a rational expression, and with that rational expression, we found that the value for x, in order to make this statement a true statement, x must be 9.
Could you do the same thing with 18 instead of x minus 6?
What's that?
Could you do the same thing with 18 instead of x minus 6?
You can, but you're taking it a step further. Okay? So you would divide by 18 on both sides, and you would end up with... So the question is, can you move the 18 and leave the x minus 6 alone? Well, you could do that, but if you...
Then you have x minus 6 equals some number because...
Well, x minus 6 would still be on the bottom, and it needs to be up
Oh.
top. It would be in the denominator, and we've got to move that, and that's why we've got to do that. Okay? So now, we're doing the same thing that we've done before, the same thing that we've done before in the past, only now we are just still taking the inverse operations, but we're doing it with polynomials, not with single digits necessarily. Okay? Does everybody understand this process? Easy enough. All right. Let's move to 9.7. Here we're going to be talking about variations. And what I want to do is I want everybody to write these three down, these three definitions, okay? You first have direct variation. Direct variation. This is when, and I want you to write this piece, and I'm going to do dv for direct variation, x equals k times y. All this means is that when y increases, x increases. Okay? When y increases, x increases. So let's look at this. If you have a the area of a circle, okay? If x is going to equal the area of a circle. Now, understand this can be applied both ways. This can also be as y increases, or as, I'm sorry, as x increases, y increases. This can be established both ways, okay? Y and x vary directly to each other. They basically go hand in hand. So if one is discussing the area, okay, and then the other one grows, if y is the area here, and if x grows or is increased by 2, well then the area is going to increase. Likewise, if x decreases, well then the area is going to decrease. So it is affected directly by x. Does that make sense? Pretty easy, right? Okay. Kind of like you and time. When time continues for 1 year, you get older for that 1 year. So you are affected directly by time. Another way of looking at it. So that's direct variation. Next we have inverse variation. Inverse variation. And this is when, if we're talking about x, then it is going to be affected inversely by y. Or, likewise, y is going to be affected indirectly by x. Since we're talking about age in ourselves, in this situation, what would happen is as time goes by 1 year, you actually get younger 1 year. The Benjamin Button effect, if y'all saw that or heard about that. So as time goes on for 1 year, you actually get younger 1 year. So it does the inverse or the opposite effect of what one does. Does that make sense? Okay. Then we have combined or joint variation. JV for joint variation. This occurs whenever both of these apply. There are more than 2 variables involved. Okay, more than 2 variables involved. Here they're interacting with each other. X acts directly with y. But in this situation, it would be like x, y, and then there's a z, or another variable that is combined with that. So not only are you, do you grow 1 year, or do you age 1 year as time goes on for 1 year, but your hair gets shorter. So now there's another variable that's involved with this, another effect. Does that make sense?
Yeah.
Okay. And your eyesight goes away, and your teeth fall out, and so all you eat is applesauce. But applesauce is good.
Especially cinnamon applesauce.
That's pretty good.
I feel bad for, sorry.
No, that's okay. But you're right. Cinnamon applesauce is good. So, consider that. Now, what's going to happen is you are going to be given information about these. Okay, you may be given a value of k and a value of x, or a value of y. Simply substitute your information into each of these and solve. It's actually not that hard, but you will see what happens. You'll see the direct variation. You'll see the opposite effect. you'll see the combined effect whenever these takes place and a combination of each of these and how they relate with each other. And that is the gist of what I'm wanting you to grasp out of this. By keeping this simple, it helps you understand concepts a little bit later on. Okay? All right, good. And then finally, 9.8 is word problems. Yes! Not only are we using functions and we're graphing, but we also get word problems. This is a full package math course. We get it all. I don't hold anything back because y'all would be disappointed if we did. Right? Absolutely. All right, so we're going to go through example 1 together instead of just saying go do word problems. You're welcome. That's what I'm about. So, everybody kind of read along and follow, and we can see how this is put together. Or you don't have to if you don't want to. If you want to try to do this without reading, because we're going to work through it, and I'm being serious about that. Sometimes it helps to just see it and not follow along in the book. Depends on the type of learner you are. A large water tank can be filled in 8 hours of continuous pumping using pump A. If a smaller pump B works with pump A, it takes only 6 hours to fill the tank. How long would it take to fill the tank using only pump B? So we have pump A, and it would take 8 hours if it worked by itself. Together with pump A and B, it only takes 6 hours. Well, what if we kicked A to the curb or quit working, and now we only have pump B? How long would it take to fill that tank with just pump B, given the information that we have? So we have pump A and pump B. Okay? And then we're going to be considering what happens when they work together. And we're building our chart from this. Now, we have information explaining how many hours it takes to do the job. Okay, hours for the job. And then we're trying to figure out the part of work that is done per hour, because we're able to take that information and isolate what we have using per hour worked. Okay, and we'll see how that comes together. Because we're looking at fractions of information. You'll see what I'm talking about here in a minute. So we're going to do part work in 1 hour. Okay, so pump A can do the full job in how many hours? 8 hours. Together it can be how many hours? 6. Now, if we look at it per hour, then pump A can do 1/8 of the job in 1 hour. 1/8. Together, they can get 1/6 of the job done in 1 hour. Now, we don't know what pump B is for the entire job. That's what we're trying to figure out. Okay? Now, that means that whenever we do find that out, we will know that it does an currently unknown fraction amount within 1 hour. Okay, we can still apply the same concept, it's just we don't know what that is just yet. Okay? Now, what we have is whenever we take 1/8 of the work and we add it, 1/8 plus the part that's unknown, we get a total package. Okay? Now, whenever we whenever we have this information, we're dealt with two problems that we've already been addressing so far this chapter. One, we have to find a common denominator, only now we're dealing with 3 fractions. But we also have an x on the bottom. Okay, we can't have the x on the bottom, we got to figure out what x is whenever it's a whole. So what do you think our common denominator is with all 3 fractions? Using all 3 fractions. What's our common denominator? First of all, what's a constant common denominator for 8 and 6?
24.
24, absolutely. Well, x has to play a factor in this as well. So we will have 24x. Okay, we're going to multiply everything times 24x. This part and this part. Okay, so each of these and this as well. We're going to multiply it times 24x and 24x. So what we have here is 24x over 8 plus 24x over x and 24x over 6. Okay? Now, in trying to find that common denominator, okay, because we're not adding these fractions right now. We're taking that concept to totally eliminate these denominators, okay? And you'll see what happens when we do that, okay? But we're taking the concept of the common denominator so that we can get rid of all of these, and in particular this x down here. Whenever we put that common denominator and multiply it up top on all 3 of them, we can now simplify each one of these. To where 8 goes into 24 3 times with x left over. X goes into 24x with just 24. And then 6 goes into 24 4 times with x left over. So do you see how we got from here to here? Okay? Now we simply subtract 3 on both sides, or 3x, and 24. So x equals 24. So pump B can do the entire job now in 24 hours. Or it would do 1/24 of the job in 1 hour. Make sense? And there we have it. Yay! All right, good job. That'll conclude today. Thank you for all the cooperation, and y'all keep up the good work.
I'll be right back.